Hello everyone. In this talk, I will present our work on fine-grained analysis on first implementations of distributed multi-rate atomic registers. I'm Kaile Huang from Nanjing University, China. In this talk, I will first introduce distributed atomic registers. Then, I will explain the first implementations of atomic registers. Our main contributions are impossibility proofs and algorithm designs for such first implementations. In distributed storage systems, data replication is widely used to improve system performance. System reliability is also improved due to the redundancy of data. However, data replication is constrained by the intrinsic problem of maintaining data consistency among different replicas. The data consistency model acts as the contract between the developer and the storage system. Only with this contract can the developers reason about and program over the data items, which actually exist as multiple replicas. Atomicity is a widely used strong consistency model. It has become the de facto standard correctness criterion for shared data access. As required by the atomicity model, operations on the shared registers appear to execute at some indivisible instant during the period of execution. Atomicity allows concurrent processes to access multiple replicas of logically the same data item, as if they were accessing one data item in the sequential manner. Though the atomic register abstraction can greatly simplify the development of upper-layer applications, their implementations often introduce long data access latency. In distributed storage systems, user-perceived latency and overall service availability are widely regarded as the most critical factors for a large class of applications. This motivates our quest for fast implementations of distributed atomic registers. In message parsing systems, current systems are widely used to model the interaction between the clients and the data replicas. From the client's point of view, the data access latency is mainly decided by the number of round trips of communications to the replicas. Focusing on the number of round trips, the design space of atomic register implementations is shown in the right figure. One round trip is obviously optimal, while we will soon see that two round trips are sufficient. Thus, when either a read or write operation implies one single round trip of communication, it is called a fast read or write. Meanwhile, we can have a simpler single write register, and we also have the more complex multi-write case. Considering the number of round trips, the design space can be viewed as the Hash diagram among possible implementations. W2R2 means that the implementation implies two round trips of both read and write operations, while all other implementations are named in a similar way. The partial order among implementations is that one implementation can have more round trips. Thus, it will provide stronger consistency guarantees while introducing longer data access latency. The famous ABD algorithm and its extension show us that two round trips are sufficient to guarantee atomicity. As for first implementations, in the single writer case, the sufficient and necessary condition for first implementations is derived, and then both the impossibility proof and the algorithm design are proposed. In the multi-writer case, it is proved impossible to maintain atomicity when both read and write operations are required to be fast. When we examine all possible implementations in a finer granularity, there are still two important open problems left. That is, whether it is possible to maintain atomicity when only either read or write is required to be first, where the other operation can have two round trips. Towards solving these two open problems, the impossibility result can be obtained when we restrict the implementation to be semi-fast, or when we change the model of computation to the 1.5 round-trip model. However, the core problems still remain open when we allow any fast read or fast write implementations. In this work, we solve the remaining two open problems and conclude this series of work on fast implementations of distributed atomic registers. For fast read implementations, we derive the necessary and sufficient condition. We also give the impossibility proof and the algorithm design. This subproblem is solved by straightforward application of the technique used in the single writer case, so we omit detailed discussion in this talk. Our main contribution is the impossibility proof for fast write implementations. To prove the impossibility of fast write implementations, we are faced with two critical challenges. First, since the read operation can now employ two round trips to communicate with the servers, the read operation now has more power to break the indistinguishability we are trying to construct. To address this challenge, we extend the traditional chain argument to a more complex three-phase chain argument in order to obtain the indistinguishability we need. Second, the first round trip of a read operation can possibly update data on the server replicas, thus affecting what other client may read. This might also break the indistinguishability we are trying to construct. To address this challenge, we sieve all the servers and eliminate the servers which are affected by the first round trip of some read operations. To derive an impossibility proof, we mainly use the chain argument. Let me first explain how a chain argument typically works by showing an example. In the chain argument, we have a chain of consecutive executions. First, look at the first execution alpha 0. In this execution, we mainly focus on two write operations. One write operation writes value 1 to all the servers, while the other operation writes value 2 to all the servers. In alpha 0, operation writing value 1 totally precedes operation writing value 2 on all the servers. Obviously, all succeeding read operations will read value 2 in alpha 0. Given the head execution alpha 0, we can obtain the next execution alpha 1 as follows. We swap the two write operations on server 1, while all other servers remain unchanged. Similarly, to get alpha 2 from alpha 1, we swap the two write operations on server 2. We can repeat this swapping process on every server and obtain the chain of executions. In our example, we have 4 servers and we have the chain from alpha 0 to alpha 4. Now, look at the tail execution alpha 4. In this execution, since all servers receive value 2 first and then value 1, all succeeding read operations will get value 1. Since in the head of the chain, read operations will get value 2, while in the tail of the chain, read operations will get value 1. There must exist some execution alpha I1 minus 1 and execution alpha I1, where read operations get value 2 in alpha I1 minus 1 and get value 1 in alpha I1. In our example, this pair of value switching executions are alpha 2 and alpha 3. Focusing on the difference between alpha 2 and alpha 3, there is only one single server 3 which can tell the difference between them, and we name this server the critical server. When the storage system is required to tolerate certain server crashes, and if we crash the critical server, then the following read operations cannot distinguish alpha 2 and alpha 3. Moreover, we focus on wait-free implementations. That is, any client eventually returns, independently of the operational status of other clients, and it will return the same value in both executions. Then, we will obtain the important indistinguishability between two value switching executions alpha2 and alpha3, and this will lead to contradiction and give us the impossibility result. Our impossibility proof is a three-phase chain argument. Our proof extends the basic chain argument we just introduced, as shown in phase 1. Since now the real operations have two round trips, they can break the indistinguishability constructed in the basic chain argument. We extend the executions in phase 1 by appending two real operations. We do the swapping between the second round trips of the newly appended real operations and obtain the chain beta. Finally, in phase 3, we construct the indistinguishability between the head and the tail executions of chain beta with the help of a relaying chain gamma. Thus, we will derive contradiction and obtain the impossibility proof. The main objective of phase 2 is to construct the chain beta. Now, we have already done the swapping of two right operations and get the chain alpha in phase 1. More importantly, we get two value switching executions alpha I1 minus 1 and alpha I1. The critical server is server I1. Chain beta is selected from two candidate chains, beta prime and beta double prime. First, we construct the chain beta prime by extension from execution alpha I1 minus 1. We append two read operations R1 and R2. Note that every read operation has two round trips, and the four round trips of the two read operations have the sequential order shown in the figure, and we will get the head execution beta prime 0. In order to construct the chain beta prime, we also do the swapping on every server. But this time, we swap the two second round trips of two read operations. Then chain beta double prime is constructed in the same way. The only difference is that beta double prime is extended from execution alpha I1. For two tail executions beta prime S and beta double prime S, we intentionally crash the critical server. Thus, R2 must return the same value in both executions, that is, either value 1 or value 2. We choose one of the candidate chain and modify it to get chain beta. According to phase 2, read operations have different return values in the head and tail executions of chain beta. So, the main objective of phase 3 is to show that read operations must return the same value in the head and tail executions of chain beta. This will lead to contradiction and give us the impossibility proof. So, when we prove that read operations in two executions have the same return value, we say that we connect these two executions. As shown in phase 3, we finally connect beta 0 and beta S. In order to connect the head and tail executions beta 0 and beta S, we need a relaying execution chain gamma. So, the critical element of our proof in phase 3 is that for every two consecutive execution beta k and beta k plus 1, we construct a relaying execution gamma k, and then we connect beta k to gamma k, and then we connect beta k plus 1 to gamma k. Repeating this process, we will finally connect the head and tail executions. Next, we explain the connecting process in more detail from the server's point of view. Our main task is to construct an execution gamma k, and we connect beta k to gamma k, and then beta k plus 1 to gamma k. In order to connect beta k and gamma k, we need another relaying execution we call temp k. The main rationale behind the construction of temp k is that we need to construct the indistinguishability between beta k and temp k, and then between temp k and gamma k. In our construction, there are two sources of indistinguishability. We name them after I finish and when I crash. First, we revise beta k to get temp k. All of the modifications are made after R1 finishes, and this will give R1 the indistinguishability. Next, we revise temp k to get gamma k. All modifications are made when R2 crashes, and this will give R2 the indistinguishability. Now, beta k and temp k can be connected. Similarly, we can connect to beta k plus 1 and gamma k through another relaying execution temp pri k. Repeating this process, we can finally connect beta 0 and beta s. Thus, read operations in beta 0 and beta s must return the same value, and this will lead to contradiction and give us an impossibility proof. In our three-phase chain argument, we assume that the first round trip of a read operation will not affect the return value of other operations. Thus, it will not break the indistinguishability we are trying to construct. Informally speaking, this assumption is quite reasonable, since in the first round trip, the reading client does not know anything about the outside world, so it should not blindly update an arbitrary variable on the servers. However, we still need to formally lift this assumption. We prove that even if some servers are affected by the first round trip of some read operations, we eliminate such servers, and our chain argument will still be connected on the remaining servers. First, look at the execution alpha 0. This time, we assume certain servers are affected by the first round trip of R2, and we call the set of these servers set sigma 1, and we call the set of the remaining servers set sigma 2. In the first phase of our chain argument, this time we do the swapping only on servers in sigma 2, and we will get a shorted chain alpha hat. We prove that read operations will return different values in the head and tail executions. Well, we will see that servers in sigma 1 behave exactly the same in both executions. So these servers cannot decide the return value and can be safely eliminated logically. So our three-phase chain argument will still be connected on the remaining servers in sigma 2, and these servers will not be affected by the first round trip of R2. In summary, we analyze first implementations of atomic registers in a finer granularity. For fast write implementation, we give an impossibility proof. For fast read implementation, we derive the necessary and sufficient condition, and we also give the impossibility proof and algorithm design. In our future work, we plan to use the knowledge calculus to reason on the impossibility proofs and the implementations of distributed shared registers. That's the end of my presentation. Thank you.